Ja.
So I think it's about time. So I would first like to welcome you all, dear colleagues, respected opponents, members of the Defense Committee, to this defense of Wu Bao Zhao's doctoral thesis. And I will start first by introducing the relevant documents and the procedure of the defense, and then we will give the floor to Wu Bao. So Wu Bao has submitted an application to the Dean of the School of Engineering for the defense of his doctoral thesis. And the title of the thesis is Molecularly Imprinted Polymer Modified Electrodes for Electrochemical Sensing of Emerging Outputs for Defense. Supervisor of the thesis is leading researcher Vitaly Savitsky, and co-supervisor of the thesis is senior lecturer Ekaterina Ret. The doctoral thesis is recommended for defense by the supervisor on 13th of June this year, and the Dean's office notes that the applicant has completed studies in the scope of the required credit points in study program chemical and materials technology. The doctoral thesis has been accepted for the defense procedure by the Dean on 13th of June 2025. Dean has also established the Defense Committee and appointed the opponents. I am Anne Rusta-Kuusk. I will be chairing this defense, and I'm also the chair of the Defense Committee. Then we have two opponents. Professor Tonika Rinke from the University of Tartu Institute of Chemistry, and second opponent Sergei Biletsky, professor from the University of Manchester, who is unfortunately not able to attend this defense today, not even online. So we will, it is possible to have a defense like this, as we have enough members in the Defense Committee. And we have written report from the second opponent, including the questions, and we have agreed with Professor Rinken that she will also provide these questions. And then also members of the Defense Committee, senior lecturer Yuri Bayev from the Department of Materials and Environmental Technology, Associate Professor Sergei Berezhnev, also from the same department, and Junior Professor Ekaterina Mazina-Shinkai from the Institute of Chemistry and Biotechnology. And the defense shall be formed on 20th of September at this very time in this room. Regarding the procedure of the defense, first we will give the floor to the applicant, who has around 20 minutes to introduce the main findings of his thesis. And then we will move to the discussion with the opponent, who has unlimited time, take as long as you need. It's Friday, so let's try to finish today. And then I will give the floor also to the defense committee members, and then also to the audience. And finally, supervisors can express their opinion. And then I will kindly ask everyone to leave the room for the defense committee to have a small discussion and make a decision, and then we will call you back in. So I hope the procedure is clear. Yes, so we may start. Bob, the floor is yours.
Good afternoon, everyone. My name is Wu Zhao, and today I will present about my doctoral work. It's a molecular enriched polymer. It's a functional polymer inside the sensor system to detect small molecules inside water. I will start with the introduction, the gap of my work, what's in the aim of my work, going with the results, and finish by conclusions. We more and more develop, but the sad thing we release also a lot of pollutant inside water. It can be big as the water bottle, or it can be very small. In my case, it's fungicide and antibiotic. They're well known for their toxicity. It causes a lot of problems for fish, plant, animal, and human. The worst thing is that there is the data to predict in this year there will be 10 million people die every year just because the problem comes from here. So for the first few steps to limit this number is the early detection in water. And a lot of techniques like HPLC or mass spectroscopy are combination of them, very well known golden standard. However, they're so expensive, they're so big, that's why scientists move on with some small sensor system can measure its inside. And in the sensor, there's some material, recognizing material in the sensor system, like biomaterial, but not all the biomaterial stable in the normal conditions. Later on, some chemical material like one layer of carbon, nanocarbon, but it may have limit selectivity. So that's what we're working on here is molecularly enriched polymer. Later on, I will connect is some material that can mimic the biomaterial, but also stable like chemical material. This is how I make it. I have one molecule, I have some monomer, and I let them bind together. And I form the polymer surrounding them, and then I remove it from the cavity. I have here some, simply say some cone on the polymer structure, but it's specific for the target in terms of size, shape, or the binding site. And this material can separate something from water, but it also can acting as the recognizing material. For example, in this case, the material nib will be formed on the working electrodes, the small circle in the middle, and this electrodes will bind to the potential site. So if the specific target bind into here, it will transform the chemical signal into electrical signal. So with some kind of response of the sensor, I can estimate what concentration inside the sample water. But if I'm using that system to detect pollutant inside water, there's some gap can be seen, like no one try to detect fungicide, azoxystrobin inside water. No one try to detect the group of similar molecules, and all the system, including these two, I need the external solution to measure the signal. So it would be nice if some system without the external solution like that. I will go further into detail later. So for each of the problem, I will have one sensor to solve that problem, to put everything inside one sentence. This tests aimed to design MIG-based electrochemical sensor for the reliable detection of single molecule, for example, fungicide, antibiotic, or a class of similar molecules like macrolide class antibiotic. This is the first article is about the sensor system to detect azoxystrobin. It's a broad spectrum fungicide commonly used everywhere in Golden Europe. But the problem is they start to present too much inside water. It's caused problem for all the living cells. The idea is there are 5 oxygen molecule atom inside the molecules, and I would like to find some monomer can form the bond to them, but it's good enough to later to form the good mid material. So I try with many different monomer, and aniline and MBD form the strong hydrogen bond toward the 5 oxygens. And all the component I will put is on the electrode. I put inside the energy enough to oxidize and form the polymer on all the monomer. However, the energy not enough to jam the template into something else. It continues to be hit here by all the hydrogen bonds surrounding. Because it's weak, it's easy to be break those bonds and leave behind the material with the cavity specific for azoxystrobin. And this is the result of characterization using infrared spectroscopic ellipsometry. This one I want to prove that the black curve represent the whole polymer structure here, and it have both characteristics of polyaniline of polyMBD. So I can confirm 2 monomer together inside here. The second reason I want to show that after the acid removal, some peak disappear or become very small. And this peak is just might also similar to the result of azoxystrobin powder. So I can confirm that azoxystrobin already removed from this structure to leave behind something like this. The second characterization is cyclic voltammetry. So I have the yellow curve, it represents for this, and since my own of this structure is non-conductive, after synthesis this, I measure, I see the oxidation peak and the reduction peak become smaller. This means that some non-conductive material already formed, but after removal by acid, the peaks start to become higher. This means it indirectly tell me that okay, some cavity inside here easy to measure the signal. And after that, with the red curve, I want to measure something in water. I put this one inside the water, and the molecule go into here again, and it become smaller again. Everything starts to be logic here. And in case of using gold electrode together with the non-conductive target, this is how my sensor works. I need to put my sensor inside the solution working at reduct probe. The idea is if I put inside the system the energy enough to oxidize ferrocyanide into ferricyanide, the electrons into here will flow into the system, result in the higher current peak. But if the non-electroactive target block here, it will be more difficult for this to extract the electron into the system, result into the smaller current peak. And the difference between them, the relative difference will be the response of the sensor. I would like this value as high as possible. This is the example. I prepared 3 sensors. The one sensor using 2 different monomer, but 2 other sensors using only single monomer. And I rebind all of them toward the same concentrations with the same time, and the sensor with the copolymer give the higher response. It means that my theory, my hypothesis about using 2 different monomers is the correct thing to do. And after some stage of optimizations, I refine my sensor with the low concentrations in both tap water and ultra pure water. Since tap water is the complex in also inside water in some article measured in Germany. The next reason is about recovery. I prepare myself 3 different bottles with these concentrations, and I using this as the calibration curve to measure them, and I have the result from the system, and it very close to the number I prepare. So I could say that my sensor has some degree of accuracy when working in the dark water. And the last reason is the idea is my sensor will give the higher response toward the target compared to other. They both of them also from this side belong to the same class as isosystolene. They have some similar in molecular structure, and my sensor give higher response in both water environments. So it means that I want to say here my sensor can distinguish the target with some other similar molecule. And moving to the second article, this is about the sensor system to detect macrolide class. Macrolide is the antibiotic class, have more members, but 3 of them usually present and also in the EU survey water lotting list. So it would be nice if some sensor can screening all of them together and no one try to do it before me, at least in the water. And the idea is they all have some ring very unique for macrolide. Since erythromycin have 4 groups, and these 2 members have 3 among those 4. So idea I will use this one to make the meat material, and then we can detect all of them together. To do this here, I need 2 different monomers. The first one is MBD. It's already published in previous work of our group. The sensor work well, but it failed to detect similar molecular structure. That's why the new thing I'm working here is as a boronic acid. Boronic acid is well known when research something have diol like glucose and so on, because in the basic or neutral environment they can form the bond. If I put the system inside acid, this bond will be free. So it just nice if I wash out this material using acid, and so I will have a mixed material, all the bond will be rich here. And of course theory that the similar molecule in this way can go inside the cavity here, not some non-target different inside shape and so on. And the reason of cyclic voltammetry show the similar logic with the previous work. The new thing I'm doing here is the additional thing is I also measure the non-debranches polymer. It's like reference material. It has similar structure like this, but they don't have cavity here. So just focus on the darker color. After synthesis, the whole polymer structure, the oxidation peak and reduction peak becomes smaller. The black curve. But after that, no matter I wash or I refine, the 2 peak not much different. It indirectly tell me that okay, no thin cone cavity here, but look like some porous, some cavity present in my materials. And after some optimization process, I can calculate and have the results of a linear application from 1.1 to 1.6 nanomole, and it's good because it's smaller than previous work. The result of recovery also good when it show the RIC value quite close to the prepared concentrations. This is about selectivity. From this graph, my sensor not only give the higher response toward the macrolide compared to other non-macrolide, but it also give the higher response if I increase the concentrations. This graph is about my sensor not only detect the single macrolide, but if I prepare all of them in the equal molarity, my sensor also give quite similar signal. The last article is it's not about the target anymore. Ampicillin belong similar to amoxicillin. It belongs to beta-lactam group with this spring and very commonly used. But the special things here is instead of gold, I'm using the new material, at least based on my knowledge, there are no group before us try to do it. So the first thing is the small example to the small experiment to see how it look like. So I put the chip, I commit the chip just for faster inside the PPS solution and run it CV. And you can see here the shape is very beautiful and very stable after many cycles. But if I add into the PPS solution some concentration of NPD, after each cycle, two peaks start to become smaller towards zero. It means that some non-conductive materials start to form, and in this case, it can only be poly-NPD because it's the only thing I add into the system. It's also good because I don't need external solution to measure, because if I put inside the system the energy enough to oxidize ruthenium, if the electron will flow into the system, it will make this one positive charge on the surface of electrons, also positive charge, and it will pull on the anion towards and on cation here. It will facilitate the current. So if in this case, this gas also non-electroactive. If nothing blocks it, it's easy to measure, to let the electron flow. It will give the higher current, but if it blocks here, it will more difficult to return something smaller. The advantage is I don't need to prepare the external solution. It will less spend money, less spend time in design, and it will cause less interference, because in literature also mentioned that the external solutions can disturb into the polymer structure. So it means that I measure not only the rebinding behavior, but I also measure the difference in the polymer structure. This is about characterizations. I use the oxidation peak of the CV. The upper part is called linear sweep photometry. And I measure both for mid and non-enriches. The only difference here is that after the washing out in mid material, I see the peak partly recover, similar to previous research logic. It indirectly tell me that in my mid material there's some cavity here. And after some stage of optimizations, I will measure it low concentration again and to calculate the limit of detections. The second bad thing about this article is I really measure it in real warm water. It was correct about 1 kilometer from here at university. And the reason is good, since the real ampicillin in water can up to 46 or 120 nanomole. The recovery also good here when the difference between the measure and the real concentration is not much. And this is about selectivity. Amoxicillin is the molecule belong to the same class with this target. This one belongs to different class. And my sensor not only give the higher response toward the target, but it also give the higher difference between mid and mid. I call it relative response here for higher for the target. So I speak a lot, but I would like to say here I mid the material I successfully combine to water with electrode to one sensor. And the evidence here is 3 separate sensors. The first one is azotistropin sensor. It's what it can detect with the low limit of detection inside water, and it can be used for agriculture applications. The second book is I successfully formed the class selective. It can combine with the electrodes. In my case is macrolide sensor. It's work well because it can be used to detect drug inside environmental water, since they intend to present many similar molecules. And the last book Using sensor, I use ruthenium dioxide at both transducer and redox probe, and seeing the sensor have low linear detection in bone water, it proved that this sensor have potential to work for monitoring the real concentration inside complex environmental water. I would like to thank my supervisor helped me from very beginning stage, and I would like to thank you also all the all my colleagues helped me during the process work. I would like to thank you all the professor, teacher, my friends, everyone from very beginning until now, organize the room and everything for me. And I would like to thank you Estonian Research Council for finance support, and to all the reviewing opponents friends complete my work to help me better, make my work better. Thank you everyone for being here today.